Agora eu vou falar pouquinho em inglês, tá bom, pessoal? Então, good afternoon, everyone. Thank you for coming to this meeting of the graduate seminar. I think this is a good opportunity for us to see what our colleagues internationally are doing, right? So today we have a very special presentation talk from Professor Luis. Professor Luis is from the University of Delft, from TU Delft. I'd like to highlight that we have a very strong collaboration with TU Delft, more than 25 years of collaboration, especially Professor Luis Cutz is assistant professor at the Department of Process and Energy in the Faculty of Mechanical Engineering, and he's developing different technologies on the conversion of biomass into fuels, into different chemicals and other topics. And today, Luis is going to give a very interesting presentation. We have been talking about this topic, the decoding digestate, data pressure, and future of the biofuels. I think this is very interesting for us in Brazil because we are very interested in biofuels. So thank you very much, Luis, for your talk. So after this presentation, we'll have a breakfast here, and we have time to discuss a little bit for time for questions. Okay. So please, Giselle, would you like to? I am just introducing Luis. I don't know.
Welcome, Luis.
Thank you. Yeah. So tomorrow they will have a meeting as well. But yeah, please, the floor is yours.
All right. Thank you, Leonardo. So yeah, I would like to start with. Let's see what's happening with the pointer. Fun, right? Okay, so I would like to start with this image. What if banana peels and spent coffee grounds from your breakfast, from your café de mañana, could be used to heat your shower tonight? I know that it sounds impossible, right? But this is basically what the biogas process does. So it basically takes all these daily leftovers like banana peels, spent coffee grounds, food waste, agricultural residues, and even manure in order to produce biogas. And it does that by letting tiny microorganisms to do the work. So in the absence of oxygen, these microorganisms break a role, and they produce this biogas that is mainly rich in methane. And methane is exactly the same molecule that we find in natural gas, with the exception that this biogas is renewable. So biogas is not only a form of methane. It also contains CO2 and other impurities that come from biomass itself, such as hydrogen sulfide, for example. But depending on the composition of methane, so if it contains between 50 and 70% of it, there is currently technology that can directly handle digestate as it is. So you can fire it in gas engines, gas turbines, to produce combined heat and power, and this electricity can be fed into the network. If we think about more advanced applications, this biogas needs to be refined. So it's usually sent to different types of upgrading stages where, for example, pressure swing absorption units, membranes, even cryogenic technologies in order to increase the purity of methane. So then we can end up with biomethane, and then this can be used in the system infrastructure, in the gas network, or it can be used in cars. So Biogas provides us with bioenergy, but the story doesn't stop there. Every digester produces two products, biogas and digestate. So I would like to ask you, what do you think happens with the digestate? Yeah, anyway.
Mostly waste.
Yes. So this digestate looks like mud. It is packed with rich nutrients that, for example, farmers they can use it in the soil and as a replacement of synthetic fertilizers. Yes, my name is Cutz from TU Delft, and today I'm going to present you some of our latest results from a grant that we got awarded from the Dutch Research Council in order to find alternatives or solutions to valorize Dutch digestate. And also, I would like to thank FAPESP, because under the FAPESP grant, or Sprint grant, I'm able to visit Leonardo, Liceo, and see you, some of you again. So let's get to it. So what you can see in this slide is the number of biogas plants per every million people in Europe. And as you can see, we have a lot of biogas infrastructure already placed in Europe, where the country that is leading in biogas production is Germany, with around 11,000 biogas plants. In the Netherlands, we have around 260 biogas plants, but it has become a huge problem for mainly three reasons. First is that we have very strict nutrient regulation regarding the nitrogen that is contained in this digestate. So we need to be very careful the amount that we put in the soil. The second is that, as you can see here, Netherlands is a very small country, so we have a very limited area. And the third is that we have a very high livestock density. We have one of the largest livestock densities in Europe. So we have a lot of people and we have a lot of cows. So we are now with a huge problem that we are producing tremendous amounts of digestate when we don't have a place to store it. If we look at how much digestate Europe is producing nowadays, so we are, let's say we're producing around 31 million tons of dry matter of digestate. In 2030, we expect that this fraction will increase in 150%, and then by 2050, this will reach around 100 or 200 million tons of dry matter. So it is highly likely that the whole Europe will struggle finding solutions to valorize digestate. So I took the liberty to see what is the status of biogas production in Brazil. And it seems that you have around 1,000 or almost 1,000 biogas plants, where most of them, they are small scale, producing around 1 million cubic meters of biogas. There are around 50 units, I think, in the country that they are capable of producing billion cubic meters of biogas. Another interesting data is that most of the biogas that you produce in Brazil comes from agriculture and then from municipal solid waste. Regarding the targets, it is expected that by 2050, the country will produce 59 billion cubic meters. This is probably, I don't know, one order of magnitude what Europe will be producing by that time. With this amount of biogas, you will be able to power 76 million of vehicles and 1.5 million of buses. So I have to be clear that digestate is not a problem in Brazil, as it is in some of the European countries. But transporting watery digestate, because digestate has a lot of water, will be uneconomical in some of these regions in Brazil. So perhaps the approach that I will show you today might be interesting for the country. So going back to our case study, the Dutch case study, this is in collaboration with one of the largest waste collectors in Europe and also in the Netherlands. So they have basically control all the digestate plants in the Netherlands, and they have two types of digestates that they produce. One is 5% dry matter, that means that it's 95% in water. And the other one is 20% dry matter and 80% water. So most of this digestate at the moment, because we cannot put it in the soil, we either export it to Belgium or we incinerate it when it's mixed with plastics. And there are some companies nowadays that they are doing, they are drying it and then producing pellets from this digestate. And then it is exported around Europe. Now, only for the Netherlands, we expect by 2030 that we will build 24 new anaerobic digestion plants, that this will translate in 0.1 billion cubic meters of biomass. So with the efficiency of our digesters, we expect that we will produce around 2.8 million tons of digestate. That is a tremendous amount of solid material. So one of the approaches that we think that might work because of the high water content of these samples is to use thermochemical conversion technologies that can take advantage of this water. And this is one of the technologies that we developed in my lab. And this, all the results that I'm going to present today were produced by my highly esteemed students. And we presented these results very recent in Italy. I think it was September, in the Biologic conference. So it's very, very fresh data. So I explained before, I think to some of you what is HCl, but I will just like explain it like very simple. So you put biomass in contact with water, and then you heat it up between 250 to 350 Celsius. And one of the peculiarities of the process is that operates at mid-range pressures. So we can operate between 5 to 15 megapascals. So at those conditions, we are able to change the properties of water. So that means that water becomes less polar. So we can dissolve, for example, easily lignin or lipids. Also the water, we can produce more protons, but also more hydroxides. So the water acts like an acid and also like a basic catalyst, and then promotes hydrolysis, dehydration, decarboxylation, all these reactions that you already know. So this is basically the scheme that we have. So we can, this technology is very versatile. It works very nice with when you have like biomass that has a lot of water, heterogeneous, but it can also handle, for example, plastics. And the main products that you get from this is a gaseous phase that has like similar composition as a biogas. We have biocrude oil or a hydrocarbon feedstock that you expect to find aromatics or alkenes, right? Then you have the hydrochar, that is this solid carbon. And then you have this aqueous phase where you would find water-soluble organics that comes from this process. So for this experimental campaign, what we did, we performed a lot of experiments, but today I'm just going to show you the ones that worked or like the ones that provided the best results. So we did several experiments between 300 and 340 Celsius, and the residence time was 30 minutes. So in 30 minutes, we were able to get like a nice hydrocarbon oil. The feedstock that we tested were between 5 and 20%. So there was no pretreatment at all. We just fed the samples as they were from renewing. So this was one of the interesting approaches in this study. You might find other HCl of digestate where you concentrate the sample, right? So maybe between 20 and 30%. In our case, we wanted to see if we didn't need to spend any energy or any costs in treating our samples. And then we performed non-catalytic experiments and catalytic experiments to see if we were able to increase the quality of these oils. So we tried different types of catalysts like amberly, zeolites, amines. And I will show you now what we got. So regarding the feedstock characterization, one of the interesting things that we found in this digestate, in Dutch digestate, is that it contains a huge amount of ash. So this huge amount of ash is problematic for all thermochemical conversion processes. And that means that in our case, we were expecting to have really low amounts of oil. But if we compare these values to recent studies in regarding HDL of digestate, you can see that it's on the range, but it's on the high in the upper bound of what you would expect to find regarding digestate. So this is the product distribution. This is basically we just put the digestate. We fix the conditions between 300 and 340, 30 minutes. And this is the results for the 5% solid. So you can see that the orange bar is gas, the green one is the hydrochar, the, let's say, black one, blue here is the aqueous phase, and this one is the bio. So as you can see, all these non-catalytic experiments yield very low quantities of oil. So the maximum that we could got with no catalyst was around 20%. Right? If you compare these values to also very recent results, in fact, all these studies that I'm citing here, we met them at a conference, and it was kind of interesting that a lot of people in Europe we are studying hydrothermal conversion of digestate. So it's a very, very hot topic at the moment. In any case, you can see that our values are within the range of what literature is producing. One interesting fact is that the no treatment of the feedstock provides higher quality of oil than compared to these results. If you see, these results from Grotola 350 is 22% yield. And this one also, 350, 15% yield. But in our case, already at 320, we already produced this 20% yield. So this was very interesting for us. Now, we weren't satisfied with these results, so we said, okay, let's try to do some chemistry in order to see if we can increase this oil yield. So we tested two different catalysts, the amberless and the zeolite for the 320 condition. And as you can see, we have there's a trade-off in the use of the catalyst. In fact, there's an antagonistic effect when we put some catalyst in our reactors, because from 20% we decrease the oil yield to 15%. So that means that it's not good, at least to try this catalyst. Now, for the 20% solids, we see also the same. And in fact, what we notice here is that increasing the dry matter content in the digestate, going from 5 to 20, we decrease the oil content. So we think this is because the effect of the ash becomes even harsher. So in the case of this sample, you can see, so this is basically all the experiments that we perform. And these are the crude oils. So after you produce this crude oil, basically what you would expect to do is that you upgrade them. So you can do that by fractionating those oils or by performing distillation. So the non-catalytic sample, you can see that 80% of it is just heavy crude oil. Basically means that this oil you cannot use it for anything else that is probably just asphalt or really not very conventional applications. But when we start using catalysis such as the amber list and even the amine for 20% solids, you can see that the light fraction and the intermediate fraction, we can increase it significantly. So we go from 20% of a valuable fraction to almost, let's say, 75%. So even though we are not able to increase the quantity of oils from our process significantly, the value of our oils increases significantly, more than threefold. So we are very happy with these results, and this is no one has tested this approach. Most of the results that you will find now in literature, they are non-catalytic, but it seems that when you start looking and doing more research on a catalytic approach, the value of these compounds gets better. Catalysts can be selected or tuned to target specific compounds. Now, if we see the elemental composition, we see that these oils, the carbon content is quite low. And when we tried the catalytic experiments for the amber list at 5%, all these samples, we see that the carbon content just decreased. So these catalysts are not doing any, let's say, nice work that we expect on our samples. So you see, this is the original carbon content of the 5% solid, but everything else is below that. So we would like to have above this mark. Now, if we see the results for the 20%, this is the benchmark. We are around, let's say, 39% of carbon content. And when we use the catalyst, the amber list, and the amine, we are able to increase the carbon content of these oils, which corresponds to the result that I showed you from the distillation, that we are increasing the quality of these crudes and probably the high heating value of these oils. So if we use the amine catalyst, we are able to retain more carbon and also preserve more hydrogen. And this is basically what you would like to find when you do hydrothermal processing or pyrolysis of this type of feedstocks. One of the challenges that we see with Digestate, and this is something that we need to study more in the coming months, is the effect of the nitrogen content. Because if this oil would be used for marine applications or for sustainable aviation fuels, you wouldn't like to fire. First of all, they wouldn't meet the criteria. Second, you wouldn't like to fire this type of oil with high nitrogen content because of the NOx. This is the result of the GCMS of our oils. And this is not for the best condition because this is still being analyzed, but this is for the 5% digestate, temperature 320, and using amine as a catalyst. So what you can see here is that we do have, let's say, better compounds that are not like heavy fraction, right? But still more work needs to be done in the catalytic approach. So these oils are mainly composed of acids, alkanes, and aromatics. So we are quite happy with aromatics and alkanes, but for sure we need to remove as much quantity of these acids. Why? Because they decrease normally the high heating value of these oils. So they are undesirable in this case. Now coming to the second most interesting product of HTL, which is the hydrochar. This is the non-catalytic approach regarding the carbon content. And similar trends regarding the ultimate analysis. We see a decrease in the carbon content. And when you calculate the OC-HC molar ratio, they are quite high. They are not able to meet any standard for certification of this charge. Now, it comes to interest again when we switch to the 20% digestate. In this case, for example, the 20% digestate, 320, using A- catalyst, we have pretty good OC-HC ratio. And in fact, these chars do qualify for certificates. So it is kind of interesting that you are producing an oil with really high quality, or let's say with decent quality, and also a hydrochar that could be useful for different types of applications. Now, if we look at the XRF of our hydrochar, we wanted to see which elements were in our material. And in this case, we see some lead, some even cadmium, some silicon, phosphorus, and chlorine. So that means that this Dutch digestate probably being mixed is mixed with maybe sewage sludge, where you can find like these heavy metals, right? So this hydrochar, even though the OC and the HC ratio meets the targets, there must be some cleaning of this hydrochar before you want to use it for anything. Now, as you can see, these results that I just showed you, they took us around maybe 6 to 8 months to produce. We perform a lot of experiments, and all this characterization requires very expensive equipment. So I think in the last visit, I think in February, Leonardo was talking about these surrogated models that they were able to predict the product distribution of pyrolysis oils, I think, right? So then we were brainstorming if it was possible to work on certain models to predict the yields and the composition of these oils. So basically, our research question was, can we predict the composition of biocrude oil from hydrothermal liquefaction with a neural network? So one of my students is working at this moment now. He has done tremendous amount of work, and I'm really impressed with this. This is not something that I used to do in my group, and now, thanks to Leonardo, we started to do this. So long story short, a neural network, I'm sure everyone is familiar with this. You require some input data, and that's basically one of the challenges of these models. And then you have some hidden layers, right? Hidden layers can be 50, can be, I don't know, thousands of hidden layers. And then you have your output layer that in this case, this is basically what you're gonna predict, right? So we had some research inspiration. There's a very nice paper for some of you that are interested in applying machine learning to thermochemical conversion in general, pyrolysis and HDL. So they were, I think, in our understanding, one of the best and the first HDL models that is capable of predicting that product distribution of HDL only based on these properties. So you only need the ultimate analysis, the ash content, and the operational conditions, and you don't need to do any experiment, and you're able to know what you're gonna get regarding the yields. So the model is fantastic. It's based on more than 520 experiments, which is very good for our field. But I think for machine learners or data scientists, it's very little data. But we need to start with something. So what is the difference between their model and what we are doing now with Jovan, my student? So basically, we are using the same input layer, ultimate analysis, operational conditions of the reactor, but instead of just stopping at the product distribution, we're going one step further. We want to estimate the bio-oil composition of these oils. So that means that if this is successful, in the future, you will not need a reactor and you will not need a gas chromatography mass spectrometer to estimate the composition of your oils. Sounds quite cool. So this is what we have done so far. So we are developing this model using Python, specifically PyTorch. The error criteria for the training is just a simple mean squared error. And the data source at this moment, it is coming from, because this is for bio-oil composition, this was tremendous amount of work for my student. So this is basically 60 full GCMS data for HDL experiments. Yeah? And this, just to brag a little bit, we put a screenshot of our model looks like, but it's very simple model at this moment. Yes, so the first thing we did with Jovan was that we needed to start from somewhere, and because we didn't have experience with this type of approach using machine learning in our group, we said, okay, at least let's try to replicate their model. So these are the results. These are the article results regarding the training data and the validation data. And this is what we get. So as you can see, regarding the training data, we are able to have similar MSE. But when it comes to the validation data, we saw that there was some gaps that we couldn't find why we had these discrepancies in the results. So the first differences that we thought about was the software. So the model of Shafizadeh is based in MATLAB. In our case, our model is using Python. Then it seems that they are throwing the data, the validation data, in a random order. So that might cause some difference within our model. And second, you can choose different initiation parameters. So that might be also a cause that our validation data is not the same extent. But in any case, as you can see, the model is quite good at this moment. Now, this is where the interesting part comes. So we were able to have the model similar to what they had, just to predict the product distribution of the HDL oils. But now we went a step further to forecast the bio-oil composition. So our layer count at this moment is 3, neuron counts per layer is 25. So this is like very, very basic, and this is basically limited because we don't have data, right? So we are using like a Ferrari to drive over like a gravel road, right? So we already talked with some of my colleagues that are experts on machine learning, and they said like, yeah, it's a very fancy approach, but if we are not able to increase this amount of data, these 60 points to, let's say, 600 experiments, then we will have things like this. So you see, like, you have the training, and then you have the validation. And this gap, the reason why you have this gap is because we are overfitting our model. So based on this trend, perhaps for our approach, we still need to see if a neural network is suitable, or we need to use maybe a regression or trying to find more simpler approach. We still it's ongoing work. Let's see. Okay, so one of the next developments for Jovan is put more work on the 2D parameters, see if we can get like a larger sample of data. Now at my lab, the other part of the group is producing experiments, but of course it's highly unlikely that we will produce 600 experiments because we also need 600 GCMS. So let's see. At the moment, we also are doing a lot of micro-scale reactors, so we can get like a kinetics and really fast experiments to see how much data we can produce while he's working on his projects. Then this model, the idea is to incorporate it into Aspen Plus. So this is also one of the things that Leonardo is working, right? And thank you for giving us this idea. So the next step for him is building this simulation. We already have in our group simulation on Aspen Plus, but now the idea is coupling them together with the model of Giovanni that is based on machine learning. So you don't need, in theory, any correlations, just very, very basic data that can take you already here. So in conclusion, I think there's something here. Last but not least, I was in a workshop maybe 3 weeks ago. It was organized by the Dutch government, and they selected around 30, 40 principal investigators to gather together to see what are the bottlenecks that are delaying the use of biofuels in Europe. So these are, for example, EC's European Commission estimates for the production capacity of drop-in advanced biofuel pathways and targets in the European Union. So I don't know if you can see it clearly, but this, in the x-axis, you can see million tons of oil equivalent. And here, you can see more or less the different technologies. You have transesterification, everything oriented to the production of biofuels. You have transesterification, you have technologies, I think, such as gasification, that this is like, in green, you have the expected capacity by 2050, and then you see pyrolysis, and then you see HDL. So when I saw this figure, I was very happy, because it seems that, of course, HDL is probably not the technology that will rule, but it is clear that it will be useful for some feedstocks, as the one I presented today. For example, with the Digestate feedstocks that have a lot of water content. I think that could be, a little bit weird. Okay, so to conclude, it seems that a catalytic approach in hydrothermal liquefaction of digestate doesn't benefit too much by increasing the yields itself of the oils, but they do contribute to reduce the heavy fraction of these oils. So we believe that much more work needs to be placed in order to select better catalysts or even synthesize, manufacture our own catalysts. We have now a working model to predict the composition. So if someone is interested in working on topics similar to this, then feel free to reach out, because this is something that we feel we have something like in order to keep pushing in this direction. And the error of training and validation is unsatisfactory for now, because of the reasons I just mentioned. So thank you for your attention. And I would like to also thank all my collaborators, students also, to help me create the work that I presented for you today. Thanks.
Thank you very much, Luis, for your very nice presentation. So we have time for questions. And maybe after this question, we have some lunch, okay? So please, go ahead.
I have two questions. First, thank you for your presentation and sharing your knowledge. The first one is related to the nitrogen content. Why can you put that nitrogen into the soil? Why the nitrogen is a problem in the Dutch case?
Yeah.
And the second one is related to another hydrothermal company, which is hydrothermal carbonization.
Yeah.
Why hydrothermal liquefaction? I mean, what advantages do those hydrothermal liquefaction have when compared to hydrothermal carbonization, because I think hydrothermal carbonization could be used also explicitly with high water content. So why did you choose this technology instead of carbonization? What are the advantages? When you compare both?
Yeah, very nice question. So regarding the first one, because we have in others we have very limited area, there is a minimum. We cannot use all the digestate that we produce because we have limited area and a lot of livestock, right? So the problem with having digestate with high nitrogen content it has a lot of ammonia. So this, when it, for example, rains or just by staying in the soil, it leaches. So it leaches to the different type of environments, like water bodies. Then you have eutrophication, and it's a huge environmental impact. The runoff and the leaching of nitrogen, and also because of emissions. Right? So we have a cap on nitrogen emission in the Netherlands, and that's also one of the reasons now we cannot build anymore, because building, for example, concrete or construction activities release nitrogen. So we are at the maximum of nitrogen level here. So now what the government is doing is buying like these farms in order to put something else that is not livestock or that is not agriculture, in order to reduce the nitrogen levels of the agriculture sector so we can build more. Regarding the second point, why we didn't go for hydrothermal carbonization, to be honest, we didn't think about it. Now that we see the results, it might seem that using HTC could be beneficial. Although these hydrochars have a lot of heavy metals that if you would like to use the carbon as it is, you need to upgrade the hydrochars. Yeah.
Thanks. More questions? I have one. As you mentioned, Luis, when you haven't used the catalyst, you got like 20% of oil yield.
Yeah. Yes.
And when you use it, the catalysts, this yield decreased, right?
Yes.
Do you think, of course, the more advanced would be done in the catalysts to produce, to increase the oil yield? Do you think it could be an interesting strategy, not using the catalyst first to produce more oil, but heavier, and then afterwards using a catalyst process to transform this oil into a lighter fraction, like to crack something like
Like a hydrotreatment, you mean?
yeah, something like that.
Yes, for sure.
It should be a
For sure.
option.
Yes. Yes.
Because when you use catalyst, you always tend to crack the oil to produce like or carbon or gas, isn't it? Because you are using a catalyst that.
Yeah, in this case, or gas, yeah. I think we're producing a lot of solids.
Yeah.
You see?
Because you are concentrating some carbon, like
It's the ash.
yeah.
We concentrate carbon, but the ash, we cannot get rid of it. Yeah, we don't crack the ash.
Okay, yeah.
Because those are
considered that.
just cadmium. Then at these temperatures, they don't go to the gas fields.
Of course.
They probably leach maybe to the atmosphere.
Okay.
Yes. But in fact, it's a good idea. I think this is an approach that we can explore for sure.
Yeah.
Upgrading the oil after.
Yeah.
Because one of the problems of using, for example, this amine catalyst, so amine is based on nitrogen. So we increase the quality of this oil, but somehow, of course, we put like maybe maximum, let's see, how much was this? 7% of catalyst with respect to the dry matter content.
Okay.
So it's not that we are putting a lot of, let's say, in weight percentage, a lot of catalyst in it, but we do put more nitrogen. So perhaps trying another catalyst after we produce oil might be even easier for the process.
Okay. Great. The And another curiosity, in that paper that you found a lot of data on GCMS.
Very good paper.
It's a very
This is only for product distribution.
For products,
It's only for
not for GCMS.
No. For the GCMS, Giovanna searched
Different sources.
Yeah.
Different sources. Yeah. Because I was wondering, if this paper or this data include distillation curves.
some of them did. Yes, some of them did.
The data
Yes.
include the distillation curves. Yeah. Because it would help us to define I would say the oil, the artificial oil, the sugarcane oil. It could help us with because if you have the distillation curve, it helps you to construct a sugarcane oil,
But if you
Inside
have
the distillation curve.
if you have already this composition,
Okay.
why do you need?
Because it is connected with the volatility of the so maybe you have like alkanes, but with the distillation curves, you can see that you have some longer alkanes or shorter alkanes. So it can help you with the definition of the size of the molecule. Maybe I don't know. Maybe.
Yeah, because one of the approaches that we are thinking now, we are just separating everything by functional groups.
Okay.
Right?
Yeah.
But the next step would be statistically
Defining
defining
what are
the changes.
Yeah, okay.
Yeah. Because the thing is, like, if you need the distillation curves, then you need more experiments.
Yeah.
So, yeah.
Of course. Good. More questions?
Thank you for delivering a very good presentation. Yeah, so I want to ask, since the main projects, if I get it right, is the reproduction of biogas, right?
Mm-hmm.
Yeah, so you just try to utilize the other product generated to maximize the use, right? The other, what do you call it now? Digestate.
Yeah. Yes.
From the beginning of the slides.
Here?
Yes.
And the whole process itself.
Yes. Yes.
This one. Yeah.
Okay, it's right. Yes, so during this anaerobic digester, you have the biogas and the digestate,
Yes.
right? Now, I want to ask that, does the quantity of digestates generated, does it affect the amount of biogas produced? Does it limit the amount of biogas that is being produced?
I think it's more dependent on the efficiency of your digester. So I think the efficiency of these digesters is like between 30 to 60%. So I think that this solid could be 60% of the whole vessel maximum. So that's the reason it is really problematic.
And so if we are having more digestate and we have two types, as you said, 5% and 20%.
Yes.
So now, according to your results, I think we have a more productive results with the 20%.
Yes.
So, so since, you clarified that the amount of digestate generated is not actually limiting the biogas produced, because I was wondering if since we can get oil from bio oil from digestates, maybe we can actually look into generating more digestates. Do you understand what I said?
Yes. So this is one of the things that perhaps I didn't mention. And so if you see this route, so the reason we use anaerobic digestion nowadays is because it's a technology that is very simple and it's very scalable. One of the drawbacks might be that you require a lot of land. Another alternative could be, instead of having an AD, you could have here HDL plant. But that would depend. So for example, some countries, like let's say like in Brazil, the countries that have vast agricultural land, producing this digestate is very useful because you can use it as a fertilizer while producing biogas that can be used for electricity or gas transport. So your infrastructure or your technology is very cheap and you have 500 products. In countries where your digestate is really low efficiency and you're producing tremendous amount of solids, then replacing AD with technologies that can get rid or not produce digestate at all makes more sense. But very nice question, thank you.
More questions?
Just curiosity, what is the size of the reactor that you use it in the extremes?
So at the moment we are working between 300 to 1.8 liters. But for example, for the machine learning, we are working with 20 milliliter. Because then we have like a dedicated reactor where we can fit like 5, 6 microscale reactors and then do the experiments to produce more data for the machine learning model. Yes.
Could you guys reproduce the results by using asking?
Results of
The results of the composition of the final problem. So, because I was wondering if a preliminary model of using neural networks could be trained by Aspen data, and then when the actual data gets, when you get more actual data, you can validate this model. But today, you can train this model using computational results from Aspen.
Yeah, so the thing is like with, at least in our experience, when we use Aspen Plus, is that you have, for example, our yield, our Gibbs, our stoic reactors. So either you need to define all the reactions, which basically for pyrolysis, HDL, or even gasification, we don't know all the set of reactions. So these models developing Aspen are very, I think they have more uncertainty what we are seeing now with the approach of the machine learning. But of course, I think you need both, because the Aspen Plus in our case is very beneficial because you have all that thermodynamic data. And of course, you can upload in Python, but yeah, Aspen Plus I think is useful. It's a user-friendly interface. You have the thermodynamic data, but it can be completely replaced, I think, by something that you develop yourself in Python. I don't know if I'm correct.
Yeah.
Yeah?
There are no specific model for HM or pyrolysis or this complex mixture in a reaction flow. There are no specific model for the Aspen or any other process simulation. This is because they are trying to train neural network to model this. It's a huge problem to model this kind of complex mixtures, reaction mixtures.
Yeah, so Aspen Plus is a tool, right, that solves a system based on equation of state. But in any case, you need to provide some data to Aspen also.
In fact, you see, there was a model predict the behavior, or HL is not necessary to do experiments and so.
Yeah, sure. If they could do the last one, you could are small with some preliminary results. Okay.
Okay, no more questions? So, okay, thank you again. Luis.
Thank you.
So we have time to have
Some coffee.
Some coffee. Yeah. Okay.
Oh, you saw that very nice stuff on the one.
Crazy. Crazy. 650%. It's very fast because, you know, the first time we talked about was like 4 months ago,
Yeah.
maybe.
So will you invite me maybe to the planet of Giovanni?
Okay, yeah, of course.
No, because he gave me the idea.
Yeah,
With this,
yeah. But you know, I have a student which that's he should be working on that. But unfortunately, he works by Petrobras. So
But that was
difficult.
we can share because
Yeah,
you know, we can share the model that we have. Maybe it can be adapted to priorities.
maybe, maybe, then maybe they can help, maybe they can like share some experience. Yeah. To use the same. Yeah, you know, because we have different data. Danielle has already different data from biology already. So we can use the same data from Danielle.
I don't know if Daniel has GCMS.
Yes, he has. I don't know how many.
Yeah.
But he has.
Yeah.
And because of that, he could develop a model.
No, I think we should stop.
Okay, yeah, the recruiting is true, yeah.
O Léo, tem que sair, então.